Think back to chapter 1. Do you remember what an absolute value graph looks like? Not this particular problem, but a regular absolute value, y equals absolute value of x. When you plug in numbers for x, the y output is always positive. So your graph is this V shape. The reason this graph matters is when we're solving inequalities, we're going to end up with two different positions where the height of the graph could be, for example, 3. We won't just have one answer when we solve absolute value problems. So let's look at our exact problem that we have to deal with. Pretend it's an equal sign for now. Absolute value of x minus 2 is equal to 3. As a reminder, when solving absolute value problems, you're always looking at solving it twice. Once when what's inside the absolute value does give an output of 3, and once when what's inside the absolute value gives an output of negative 3. So we'll have to add 2 on both sides of our equation. We get x equals 5 and x equals negative 1. These are our boundary points. Because it's an absolute value, we're going to have to change those equal signs later, and we're going to use a number line to help us decide what direction they should face. So we're going to start by looking at our inequality symbol. Since it did not have the equal to line, that means we're going to have open circles as our boundary points, strictly greater than or less than 5, and strictly greater than or less than negative 1. Now when you look at this V-shaped graph, there's really only two options for where the solutions could be. The solutions could be inside the V between the 2 points here, or the solutions could be on the outsides of the graph, out here and here. So you can test any point, not negative 1 or 5, that's inside the points or outside the points, and see if that's a solution. So for example, I'm going to pick 1 as my test point. If I plug in a 1 to the original equation, as x, negative 1 minus 2, positive 1 minus 2 is negative 1, and the absolute value of negative 1 is 1, and 1 is greater than 3. No, that is false. 1 is not greater than 3. So inside here should not be shaded, and the answers we have are on the outsides. Meaning, any number smaller than 1, so negative 2, negative 3, negative 4, would make the inequality true, and any number bigger than 5, 6, 7, 8, would also make the inequality true. So we still need to write our final answer. X has to be smaller than negative 1, or x has to be bigger than 5. We won't solve every one, we'll just do problems A and B. So if we start with problem A, we know x plus 2 is less than 1, and we're going to put it as an equals for now, and we've got x plus 2 could be negative 1, or x plus 2 could have an output of negative 1 when we do the inequality. We're going to minus 2 on both sides, and we get x could be negative 1, or x could be negative 3. These are our boundary points, not our final answer. So we go to our number line, 0, negative 1. And once again, we have a strictly less than symbol, not an equal to. So we're going to start with open circles at negative 1 and negative 3. And then we can test a point in between them or outside of them. I'll try testing negative 2 and we'll see what happens. If we put negative 2 into the original, negative 2 plus 2, absolute value, is that less than 1? Absolute value of 0 is 0. Is that less than 1? Yes. So our shading will be inside the boundary points. And to write our inequalities, You can write two separate inequalities, or you can compound it because it's one region in between 2 points. So our region would be that the x's are in between -3 and -1. And then the symbols are showing this direction, saying -3 is the smallest and -1 is the greatest. Or if that makes you uncomfortable, you could write them separately. You could say x is greater than -3 and x is less than -1. That would be fine too. Our last example is going to be a quadratic. Problem B. Anytime you have a quadratic, in order to solve it, even if it was just an equal sign, you need to use factoring or quadratic formula or complete the square. As a teacher, I can factor this in my head. I'm not going to show any work, but you would do the diamond and rectangle factoring, or you could do quadratic formula. So it factors into x plus 4 and x minus 3. And I get 2x equals solutions using the zero product property of -4, because -4 plus 4 would make 0, and of +3, because +3 minus 3 would make 0. So we make our number line. 0, 1, 2, 3, -4. Ours was strictly less than in the original, so we'll have open circles. But a parabola is a U-shaped graph. So just like our previous examples, we are going to have an option to be below 0, less than 0, either in between the two boundary points or outside of the two boundary points. So I'll test the point in between, which I think is the correct answer. So let's try plugging in 0 to the inequality. 0 squared plus 0 minus 12, is that less than 0? -12 is less than 0. Yes, that is true, so I would shade in between my boundary points, and I write my final answer as an inequality. I'm going to put it as a combined compound inequality again, because it's one region where the x's are stuck in between. The smallest is -4 and the greatest is +3.